G'day guys, Mr. Bennett here. Today what we're going to do, we're going to be talking about charges and electric fields, and we're going to also be looking at the concept of a electron volt. Alright, so now we all have used Coulomb's law, okay, so the main thing there is what we're looking at is that the force is directly proportional to Q1 and Q2, and we have the force that is inversely proportional to the radius squared. And we keep seeing that inverse proportionality all the time, which is fine, but yeah, so you just need to be aware about all that. Now we know that the electric field strength is equal to the force over the charge. Now quite often they, instead of using Q, they use the term E, right? E for the electron, the charge of electron. Now we know the charge of an electron is in fact equal to 1.6 by 10 to the minus 19 coulombs. Right? So that's also the same charge as a proton as well. So if we want to find the electric field strength, what we do is, if we've got our particle here, this is a positive particle, what we're going to use is a particle at a distance r, and we're going to use a thing called a test charge. Right? So therefore, if we use that test charge, which is a plus 1 Coulomb charge, then the electric field, right, becomes equal to simply that test charge over that test charge up there, and so therefore it's 1 over 4 pi epsilon, and it's Q all over r squared. And that's a formula that you'll find on your formula sheet. So if they say to you, what is the electric field near a point charge, you simply go how far away from the point charge you are, and you can simply plug in the value of the charge itself, and you can work out what the electric field strength is. Now, as I tried to explain in class the other day for people, is that I'd like you to think of the electric field and the gravitational field being very, very similar. Alright, so if we have just imagine having a big plate, alright, like that, and we have another big plate down the bottom here. Alright, so we've got two big plates. For this big plate, we're going to put a negative charge on it, and this one here we're going to have a positive charge. Technically, what that might mean is that this here has 2000 volts, and this one over here might be 0 volts. Okay, so we've got two plates, and what happens in here then, we've got field lines going from positive to negative, don't we? So we've got in here a uniform electric field. Alright, so there's a uniform electric field in here, and obviously it's three-dimensional. When we start talking about doing these things here, quite often we'll just represent that by a side view. Alright, so all you need to do there is basically draw your two parallel plates. Right, and then you go 0 volts and you go 2000 volts. So you go negative and positive, and you can draw your field lines. Now in here, you evenly space them. Right, if you evenly space them, that represents a nice uniform electric field. Okay, and then at the end, what will probably happen is you get a little bit of distortion with that, a little distortion at the end there. Alright, so what happens in here in terms of a gravitational field or electric field? And as I went through the other day, and I just want to reiterate that, let's say we had an electron in here, and our electron's moving upwards, right? It doesn't want to go that way, right? Eventually, if you fire it up that way, it's going to turn around and head back towards the positive plate. That's our little electron. If we've got our electron coming in at an angle like that, then that electron will follow a parabolic path, okay, and hit the plate over there. So the key thing is, like as the gravitational field, the electric field behaves exactly the same thing. If we talk about gravitational potential energy, what happens there is that we move something a mass. We move a mass from, you know, a particular height, right, and we move it upwards. As we move that upwards, it gets gravitational potential energy, right? Well, what we're looking at here is, as the electron moves up that way, upwards that way, it gets electrical potential energy, right? And the symbol we're going to use for that is, well, it's really that energy is the work, okay? So work and energy are the same things. So in your particular notes, you can find a formula which says Q delta V, right? This refers to the potential difference, and really what that means is the difference in voltage, and that there is the charge. And obviously we're talking about this term here, which is work. So the work is always measured in joules. Alright. So a really useful term that we want to look at is a thing called a 1 electron volt. 1 electron volt is equivalent to moving an electron through a potential difference of 1 volt. So a 1 electron volt is the energy that's gained by moving an electron through a potential difference of 1 volt. Alright, so what we know is 1 electron volts equal to 1.6 by 10 to the minus 19 joules. Okay, so it's a really small value. Now that's really useful when we start talking about electrons and how they interact. Alright, so potential difference is a really important concept. The electron volt is a really important concept as well in terms of the units that we use throughout our understanding of electrons and how they behave. Alright, so this video obviously is the first video of this, of the series in terms of looking at electric fields, and I think it's really important that you find a way of remembering this definition here. I don't want necessarily you to learn it by heart, but in your book there's a couple of nice derivations or definitions for you to understand about that. Alright, we'll leave that video for today right here, and I'll see you next time.